You probably assume that the oldest thing in the universe must also be the most worn out, aged by all the time it has lived through. But the oldest light in existence has, by its own reckoning, not aged a single second. A photon travels at the speed of light, and at that speed, time does not pass at all. So the relic light that was set free when the universe was 380,000 years old, the light we measure as almost 14 billion years old, has experienced no time whatsoever between its birth and the instant it lands on you tonight. It is ancient and ageless at once, drained almost to nothing and yet immortal in its own frame. How can the same light be both the oldest thing you will ever meet and a thing that has never aged? Get cozy, subscribe if you're new here, because by the end of this, you will see why light may be the closest thing the universe has to something that cannot die. Let's slowly settle into this. Part 1. The light that never left. There is a kind of light falling on you right now that is older than the sun. It is older than the earth, older than every atom of carbon in your hands, older than the oldest stone on the oldest mountain. It was already ancient before the first star caught fire, and it is not sitting in a museum somewhere, sealed behind glass. It is in the room with you tonight. It is passing through the walls, through the window, through the air in front of your face, and a faint patter of it is landing on your skin as you breathe. You cannot feel it, you cannot see it, but it is there, and it has been there your whole life, and it will still be arriving long after you, and everyone you have ever known are gone. This light has a strange property that we are going to spend the next couple of hours sitting with. It is the oldest light in the universe, and yet, in a sense, we will come to understand, it has barely aged at all. It has travelled for almost 14 billion years, and it has lost almost all of the energy it was born with, and somehow it is still here. Not a memory of light, not a record of light. The actual, original light itself, the same photons that were set free when the universe was newborn, still streaming through space, still landing, still cooling. So tonight I want to ask a question that sounds simple and turns out to be one of the strangest in all of physics. Does light ever die? When the universe makes a beam of light, what happens to it in the end? Does it last forever, travelling on and on until the end of time? Or does it slowly fade away into nothing? You might think this is the sort of question we settled long ago. It is not. The answer pulls on threads that reach into the expansion of the universe, into the meaning of energy, into the nature of time itself, and into the far future of everything that exists. By the end of tonight, the word death is going to mean something different to you than it does right now. Let me start with something you may have actually seen with your own eyes, without knowing what you were looking at. If you are old enough to remember televisions with antennas, the kind that picked up channels out of the air, you will remember what happened when you turned the dial to a channel that was not broadcasting. The screen filled with snow, a storm of black and white static hissing out of the speaker, flickering chaos with no picture in it. Most of that noise came from ordinary things, from electronics and distant signals, and the warmth of the set itself. But a small fraction of it, roughly 1% of that snow, was something else entirely. It was the oldest light in the universe, arriving from every direction in the sky at once, ending a journey that began before the Earth existed by nudging a few specks of static onto a screen in someone's living room. That is not a metaphor. That is literally true. The relic light of the early universe was landing in homes all over the world, and people were tapping the top of the television and adjusting the antenna, trying to make the afterglow of creation go away so they could watch their program. We will come back to how we first learned that this light was there, because the story of its discovery is one of the most human and accidental moments in the history of science. But I want you to hold on to that image for now. The beginning of the universe, showing up as static. The oldest thing you will ever encounter dismissed as noise. This light is called the cosmic microwave background, and it is the central character of tonight's story. Every cubic centimetre of space around you, a volume about the size of a sugar cube, contains roughly 411 of these ancient photons. Multiply that out across the room, across the sky, across the observable universe, and the numbers become difficult to hold in the mind. By sheer count, almost all the light in the universe is this relic light. The light from all the stars in all the galaxies, all the campfires and candles and screens and suns, is a faint sprinkle on top of an ocean of this older glow. We live, all of us, immersed in it. We always have. And here is the first crack in the simple picture, the first hint that our question is not as easy as it sounds. This light was born hot. When it was set free, it glowed at a temperature of around 3,000 degrees, a warm orange-white glow like the surface of a cooler star. Bright enough that if you had been there, the whole sky in every direction would have shone like the inside of a furnace. That same light, those same photons, now glow at a temperature of just 2.7 Kelvin. That is 2.7 degrees above absolute zero, the coldest temperature that can exist. The light has gone from the warmth of a glowing ember to a cold so profound it is almost the absence of warmth altogether. It has lost more than 99.9% of the energy it was born with. So which is it? Is this light alive or dead? It is still here. There is no question that it is still here, in enormous numbers, filling all of space, but it has been drained almost to nothing, cooled to a whisper, stretched until it can barely be detected at all. Something happened to it over those billions of years, something that took nearly all of its energy and left the light itself behind, like a fire that has gone out, but whose glow you can somehow still see. To understand what happened, we are going to have to follow one of these photons from its birth to the present day, and then onward into the far future to see how the story ends. I want to make you a promise about the shape of tonight, because I think it will help you settle in. We are going to take this slowly. We are not going to rush from fact to fact. We are going to follow a single particle of light across the entire history of the universe, and we are going to stop along the way to ask what is really happening to it and what it means. There will be moments that feel like standing inside the early universe, and moments that feel like floating at the end of time, and moments where law of physics you have trusted your whole life quietly bends in front of you. If you drift off somewhere in the middle, that is all right. This is a long story, and it is meant to keep you company, not to keep you awake, because that is what this light is, in the end. It is the universe's longest goodbye. It is a glow that began before there were any eyes to see it, and it has been fading, gently, patiently, for almost 14 billion years, and it is not finished yet. It will not be finished for a very long time. To understand why, we have to go back to the moment this light was made, to a time when the universe was a different place than anything you have ever known. We have to go back to the fog at the beginning of everything. Part 2. The fog at the beginning of everything. Imagine the universe when it was very young, not at the very first instant, not at the moment of the Big Bang itself, which is a separate mystery for another night, but a little while after, when it had settled into something we can actually describe. The universe at this age was not empty and dark the way space is now. It was filled, everywhere, with a hot, dense, glowing soup of particles. There were no stars, there were no planets, there were no atoms, not yet, not in the form you would recognize. There was just an ocean of bare particles, packed together, hot enough to glow, stretching in every direction without end. The temperature of this early universe was thousands of degrees, hot enough that matter could not hold itself together in the ordinary way. You know that an atom is made of a small heavy nucleus with electrons around it. In the early universe, it was too hot for that arrangement to survive. The moment an electron tried to settle into place around a nucleus, a passing burst of energy would knock it loose again. So the electrons roamed free, unattached, drifting through the soup as a separate population, and the nuclei drifted free as well, and nothing could combine into the neutral atoms we are made of today. This state of matter, where the electrons are stripped away and everything is electrically charged and loose, is called a plasma. The early universe was a plasma, everywhere, all at once. Now here is the thing about a plasma that matters for our story. A plasma is opaque to light. Light cannot travel through it in a straight line. To understand why, you have to know one fact about photons and electrons. A photon, a particle of light, cannot resist a free electron. When a photon meets a free-floating electron, it scatters off it, bouncing away in a new direction, the way a cue ball glances off another ball on a table. In the plasma of the early universe, free electrons were everywhere, packed close together, and so a photon could not get anywhere. It would travel a tiny distance, slam into an electron, change direction, travel another tiny distance, slam into another electron, and change direction again. The light was trapped, ricochet endlessly inside the fog, never able to break free and travel in a clean straight line. If you had somehow been able to float inside the universe at this age and survive the heat, which you could not, you would have seen a featureless glowing fog in every direction. There would be no distant objects to look at, because you could not see through the fog to anything far away. The light reaching your eyes would have travelled only a short distance before, scattering, so you would be wrapped in a glowing blankness, like beings inside a cloud lit from within, or like standing inside the body of the sun. The whole universe was like the inside of a star, bright, hot, and completely closed in. It is worth pausing on just how crowded that early universe was with light, because it tells you why the fog was so total. For every single particle of ordinary matter in the cosmos, every proton and every electron, there were, and still are, well over 1 billion photons. The universe has always been, by sheer count, overwhelmingly made of light rather than matter. So in the plasma era, each free electron sat in a dense storm of photons, battered by them from every side, while each photon in turn could cross only the smallest distance before meeting the next electron. Physicists can calculate that distance, the average gap a photon travelled between one collision and the next, and in the packed early universe, it was almost nothing at all. The light was not so much travelling as trembling in place, handed from electron to electron, going nowhere on the whole, even as each individual photon moved at the full speed of light. A photon released near the centre of that fog might take thousands of years to work its way outward across a region it could have crossed in an instant if the path had been clear. And the clearing, when it came, was not perfectly sudden. I have been describing recombination as a single moment, the instant the fog lifted, and on the scale of the universe's whole life, it was indeed brief, but it was not instantaneous. The temperature fell through the critical range over a span of a few thousand years, and during that span the electrons were captured into atoms gradually, a few more with every passing century. So the fog did not vanish all at once, but thinned steadily, like a morning mist burning off rather than a curtain dropping. There is even a slight subtlety in the order of things, because helium, which formed in small amounts in the first few minutes of the universe, captured its electrons a little earlier than hydrogen did, the hydrogen being the last and largest population to finally go neutral. The result is that the surface of last scattering is not a razor-thin shell, but a layer with a real, if modest, thickness. the zone over which the universe finished the long work of becoming clear. When we look at the oldest light, we are looking at the far side of that thinning mist, at the last electrons, letting go of the last photons as the fog gave up its hold, and it was getting bigger. This is the part you have to keep in your mind for the rest of the night, because it is the engine of everything that follows. The universe was expanding. Space itself was stretching, growing larger in every direction, carrying the soup of particles apart from itself. And as the universe expanded, it cooled. This is a simple relationship that we feel in everyday life in reverse. When a gas is compressed, it heats up, and when it expands, it cools down. The universe was expanding, so the universe was cooling, slowly, steadily, over hundreds of thousands of years. The fog was getting colder. Then, when the universe was about 380,000 years old, the temperature dropped to that magic number we mentioned earlier, around 3,000 degrees. And at 3,000 degrees, something changed that would set our light eye free. At that temperature, finally, the bursts of energy flying around were no longer strong enough to knock electrons loose the instant they settled. For the first time in the history of the universe, an electron could fall into place around a nucleus and stay there. Electrons combined with nuclei, and neutral atoms formed, hydrogen and a little helium, across the entire universe more or less at once. This event has a name. It is called recombination, although that name is a little misleading because the electrons and nuclei had never actually been combined before. It would be more honest to call it the Great Combination, the moment the universe first assembled itself into atoms. And here is why it matters for the light. When the free electrons vanished, captured into atoms, the fog cleared. Suddenly, there were no more loose electrons for the photons to scatter off. A photon that had been trapped, bouncing endlessly for hundreds of thousands of years, suddenly found the path ahead of it open. It could travel in a straight line, on and on, without slamming into anything. In a cosmically brief window, the universe went from opaque to transparent, from a closed glowing fog to a clear space you could see across. The light was set free. This is the birth of our photon. The moment of recombination is when this oldest light we can ever detect was released to begin its journey. And there is a beautiful name for the place this happened. We call it the surface of last scattering. It is the last moment, the last place, where these photons touched matter, where they bounced off that final electron before the fog cleared and let them go. Every relic photon we catch today carries the imprint of that final scattering, almost 14 billion years ago. When we look at the cosmic microwave background, we are looking at the surface of last scattering. We are seeing the exact moment the universe became clear. I want you to sit inside that moment for a little while, because it is one of the most extraordinary moments in all of existence, and it deserves more than a sentence. You are a single point of light, and you have never gone anywhere. For as long as you have existed, hundreds of thousands of years, you have been trapped in the glowing fog. You are born, you travel the smallest possible distance, you strike a free electron, and you scatter. You are absorbed and released, knocked in a new direction every time, never moving more than a hair's breadth before the next collision. Around you in every direction is the same featureless orange furnace, 3,000 degrees, pressing in with no gap and no opening anywhere. This is all you have ever known, a bright, hot, closed world with no distance in it. Then the furnace cools, just slightly. The electrons around you begin to vanish, pulled into atoms, one after another, faster and faster. The collisions that have defined your entire existence begin to space out. There is a longer gap before the next one, and a longer gap. And then, for the first time, the path in front of you simply opens. There is no electron waiting. There is no fog. There is a clear, straight road ahead. stretching out farther than you have ever been able to see, and you are moving down it at the only speed you have ever known, the speed of light, and nothing is stopping you. The furnace falls away behind you. The universe has become clear, and you are free, and you are traveling, and you will not be stopped again for a very, very long time. That is the moment our light was born into its freedom. But the universe it was set free into was not the calm, settled, mostly empty space we know today. It was young, and it was small, and it was still growing. And as our photons set out across it, that growth was about to do something to the light that would take almost everything it had. To understand what happened next, we have to look closely at what it means for space itself to stretch. Part 3. Set free into a growing dark. Our photon is travelling now. The fog is gone, the road is clear, and it is moving in a straight line at the speed of light, the way light always moves and always will. But I want to correct a picture that almost everyone carries in their head without realizing it, because if you keep that picture, nothing about the rest of tonight will make sense. The picture is this. Most of us imagine space as a kind of empty stage, a fixed, unchanging arena, and we imagine things moving around inside it. The stage stays the same size and the actors walk across it. That is how space feels in everyday life. The room you are in is not growing. The distance to the wall is the distance to the wall. But on the scale of the whole universe, that picture is wrong, and the truth is much stranger. Space is not a fixed stage. Space itself is growing. The arena is expanding in every direction all the time. This is one of the most well-established facts in all of science, and it is worth saying slowly so it can sink in. The distance between far apart things in the universe increases not because they are flying apart through space, but because the space between them is itself getting larger. New space, in a sense, is appearing between the galaxies, gently pushing them apart, everywhere at once. It helps to use a picture here, because the idea is so far from anything we touch in daily life. Imagine you have a loaf of raisin bread dough, with raisins scattered all through it, and you put it in a warm place to rise. As the dough expands, every raisin moves away from every other raisin. A raisin on one side of the loaf sees all the other raisins receding from it. But no raisin is special, no raisin is at the center, and no raisin is actually traveling through the dough. They are all just sitting in place while the dough between them swells. The raisins are the galaxies, the dough is space, and the rising is the expansion of the universe. Now, our photon is not a galaxy. It is light, and it is not sitting in place. It is moving, racing across the dough at the speed of light, trying to get somewhere. But the dough it is crossing is rising the whole time. And this is where the trouble begins for our light, because the expansion of space does something to a travelling photon that it does not do to a thrown ball or a flying spaceship. It does not just carry the photon along. It reaches inside the light itself and stretches it. To see why, you have to remember what light actually is. Light is a wave. A photon is a ripple in the electric and magnetic fields. A little travelling crest and trough, and like any wave, it has a wavelength, the distance from one crest to the next. The wavelength of light is what determines its colour and its energy. Short wavelengths, where the crests are packed close together, are high-energy light, the blue and violet and beyond. Long wavelengths, where the crests are spread far apart, are low-energy light, the red and the infrared and beyond. A photon's wavelength is its identity. It tells you everything about how much energy that photon carries. So, here is what the expansion of space does. As our photon travels across the growing universe, the space it is riding through is stretching, and the wave stretches with it. The crests of the wave get pulled farther apart because the space between them is expanding, just like the space between the raisins. The wavelength grows. And remember what a growing wavelength means. It means the light is sliding toward the red, toward the infrared, toward lower and lower energy. The expansion of the universe is, quite literally, stretching the light out and draining its energy, turn by turn, year by year, for billions of years. This effect has a name you have probably heard. It is called redshift, because the stretching shifts visible light toward the red end of the spectrum, where the wavelengths are longer. But redshift is not just about the color red. It is a continuous, relentless process that affects every photon traveling across the expanding universe, stretching its wave longer and longer, bleeding its energy away. The more the universe expands while the light is traveling, the more the light is stretched, and the more energy it loses. And our photon, born at the surface of last scattering almost 14 billion years ago, has been traveling for nearly the entire history of the universe. It has been stretched for as long as anything can be stretched. The universe has roughly 1,100 times more space in it now than it did when our photon was set free, and so our photon's wavelength has been stretched by that same factor, around 1,100 times longer than it was at birth. I want to make sure the link between wavelength and energy is solid in your mind, because everything tonight turns on it, and it is not something most of us were ever taught. A photon's energy is not about how fast it moves, because all photons move at exactly the same speed, the speed of light, always. A photon's energy is about its wavelength alone, a short wavelength. With the crests of the wave packed tightly together is a high-energy photon, the kind that can pass through your skin or fog a piece of film, the ultraviolet and the X-ray, and beyond. A long wavelength, with the crests spread far apart, is a low-energy photon, the kind that can barely warm anything at all, the infrared and the microwave and the radio. So, when the expansion of space stretches a photon's wavelength, spreading its crests apart, it is not merely changing the photon's color as a matter of appearance. It is draining the photon's energy in direct proportion. Double the wavelength and you halve the energy. Stretch it 1,100-fold, and you are left with roughly 1 part in 1,100 of the energy you began with. The reddening and the draining are the same event, described 2 ways. There is a way of measuring the stretch that astronomers use as a kind of universal timestamp, and it is worth knowing because you will hear it everywhere in this subject. They call it redshift, and they give it a number. A redshift of 1 means the wavelength has doubled since the light was emitted. A redshift of 9 means it has stretched tenfold. And the oldest light, the cosmic microwave background, carries a redshift of about 1,100, the largest redshift of any light we can ever catch, because it has been stretching for longer than any other light in existence. That single number, 1,100, encodes the whole journey. It tells you how much larger the universe has grown since the fog cleared, how much the light has reddened, and how much of its birth energy is gone. One number, holding almost 14 billion years of patient stretching. Let me put that in terms you can picture. When our photon was released, its wavelength placed it at the edge of visible light, a warm glow you could almost see, bordering the near-infrared. By the time it reaches us today, after all that stretching, its wavelength has grown to around 1 to 2 millimeters. That is no longer visible light. It is no longer infrared. It is a microwave, the same kind of low-energy light your microwave oven uses, except far, far fainter. The light that was born glowing has been stretched into faint microwave hum. That is why we call it the cosmic microwave background. The microwave part is not how it started. It is what almost 14 billion years of expansion did to it. And this is the moment in our story where the question of tonight first shows its teeth, because if the universe is stretching our light, year after year, draining its energy turn after turn, then it certainly looks like the light is dying. It started as a brilliant glow, and it has faded to a cold microwave hum. Stretch it long enough, you might think, and surely the energy will reach zero, and the light will simply be gone. Is that what is happening? Is the expansion of the universe slowly killing the oldest light, draining it drop by drop until there is nothing left? It is a reasonable fear. It is exactly the conclusion the picture seems to demand. But before we can decide whether the light is dying, we have to answer a question that turns out to be far deeper and far stranger than it first appears. When the light loses all this energy, when the expansion of space drains 99.9% of what the photon was born with, where does that energy go? Energy is supposed to be the one thing the universe never loses. It can change form, we are told, but it can never be created or destroyed. So if our light is losing energy, that energy has to be going somewhere. It has to be turning into something, hiding somewhere, waiting somewhere. The trouble is, when you actually go looking for it, you cannot find it anywhere at all. And the reason why is going to bend one of the most trusted laws you know. Part 4. The long stretch. Let us stay with our photon as it travels, because the stretching we just described is not a single event. It is a process that goes on for the entire journey, and the slowness of it is part of what makes it so strange. Our light is not stretched all at once in some sudden snap. It is stretched continuously, gently, every moment of every year for almost 14 billion years, by an amount so small from one moment to the next that nothing about the light seems to be changing at all. And yet the changes accumulate and accumulate and accumulate until the warm glow of the early universe has become a cold microwave hum. Nothing dramatic ever happens to our photon. It simply rides the swelling of space, and the swelling does the rest. I find it worth slowing down here and travelling alongside the light for a while, because the scale of the journey is almost impossible to feel from the outside. You are the photon now. You have just been set free from the fog, and the road ahead is open. You are a warm orange ripple, travelling at the speed of light, and the universe around you is young and small and crowded. For the first stretch of your journey, the space around you is thick with the new neutral gas, the hydrogen and helium that just formed, although it no longer stops you, because the electrons are bound up in atoms now and cannot scatter you the way they used to. You travel, and the space you move through swells beneath you, and your wave lengthens by a fraction you could never notice. Millions of years pass. So you are still orange, but a deeper, redder orange now, sliding toward the colour of a dying coal. The universe around you darkens. For a long age after the fog cleared, there were no stars at all, only the cooling gas and your own fading glow, and historians of the cosmos call this stretch the dark ages, a time when the only light in existence was the relic light, you and your countless siblings, all reddening together. Then, far away, the first stars ignite, the first galaxies begin to gather, and the universe fills slowly with new pinpoints of light. But you do not stop for any of it. You travel on, past forming galaxies, through the growing web of matter, and your wave keeps lengthening. You slide from red into the infrared, and now no human eye could see you at all. Hundreds of millions of years become billions. You are no longer a glow. You are a long, slow microwave ripple, carrying 1,000th of the energy you set out with. And still you have not slowed. Still you have not stopped. Still you are travelling at exactly the speed you have always travelled, toward a small blue world that will not exist for most of your journey, and whose oceans and creatures and televisions are still billions of years away. That is what the long stretch feels like from the inside. If a photon could feel anything, which is a question we will come back to in a stranger form later tonight. From the outside, from our point of view, the numbers are clean and almost unbelievable. The universe has expanded by a factor of about 1100 since our light was set free. So the wavelength of our light has grown by a factor of about 1100. And because the energy of a photon is inversely tied to its wavelength, the energy of our light has dropped by that same factor of about 1100. More than 99.9% of the energy each relic photon carried at birth is simply no longer there. Now, I want to be careful and precise about what is and is not happening, because there are two different ways light can lose energy in the universe, and only one of them is at work here. The first way is the ordinary way, the way you already understand. Light can lose energy by interacting with matter. It can be absorbed, where its energy is handed over to an atom or a molecule, and the photon ceases to exist as light. It can scatter off particles and lose a little energy in the exchange. This is how a warm object cools, how sunlight heats your skin, how the light from a distant lamp is dimmed by fog. In all these cases, the energy goes somewhere obvious. It becomes heat, it becomes motion, it becomes some other form you can point to. The book's balance. Nothing is mysterious. But that is not what is happening to our photon. Our photon, since the moment the fog cleared, has mostly not interacted with anything at all. It has travelled through the emptiness between the galaxies, untouched, unabsorbed, unscattered, for almost the entire age of the universe. It did not hand its energy to any atom. It did not warm anything up. It did not collide with anything and lose energy in the exchange. It simply rode the expansion of space, and its wavelength grew, and its energy fell. This is the second way light can lose energy, and it is unique to the expanding universe. It is called cosmological redshift, and it is not like anything else. The light loses its energy not to any object, not to any process you can name, but to the stretching of space itself. And this is where the simple, reasonable story we have been telling runs straight into a wall, because we have a law, one of the most cherished laws in all of physics, that says energy can never be created and never be destroyed. It can only change from one form to another. The heat in your coffee, the motion of a falling stone, the chemical energy in food, the light from the sun, all of it can transform endlessly, but the total amount, we are taught, never changes. This is the conservation of energy, and it is so reliable, so deeply confirmed in every laboratory experiment ever performed, that physicists treat any apparent violation of it as a sign that they have made a mistake somewhere. So when our photon loses 99.9% of its energy to the stretching of space, the law of conservation of energy steps forward and demands an answer. That energy cannot simply have vanished. It must have gone somewhere. It must have been handed to something, stored in something, converted into something. If you believe in the conservation of energy, and almost everyone does, and for very good reason, then there has to be a hidden account out somewhere that has grown larger by exactly the amount our light has lost. Find that account and the mystery dissolves. The light is not dying. It is just paying its energy into a piggy bank we have not looked inside yet. It is a perfectly natural thing to expect. It is what energy always does in our experience. And so generations of curious people, on first learning about cosmological redshift, have asked exactly this question. The energy of all this stretched light, the energy of every photon in the cosmic microwave background, and every photon from every distant galaxy, all of it bleeding away as the universe expands, where does it go? It is one of the best questions you can ask about the universe. And the answer, when you finally chase it all the way down, is one of the most unsettling in all of physics. Because when you go looking for the hidden account, for the place the energy is stored, you find that there is no account. The energy does not go anywhere. It is not transferred. It is not hidden. It is simply gone. And to understand how that can possibly be true without breaking the universe, we have to look very carefully at what the law of conservation of energy actually says. and at the one condition it quietly depends on. Part 5. Where the energy goes when it goes nowhere. I have to tell you something about the conservation of energy that is almost never mentioned when you first learn it, and it changes everything. The law of conservation of energy is true, but it is true only under a specific condition, and that condition is so reliably met in everyday life that we forget it is there at all. We are taught the law as though it were unconditional, a flat statement that energy is always conserved, full stop. But the deeper truth, the version written into the foundations of physics, comes with a clause attached. And once you see the clause, the mystery of the disappearing light begins to resolve into something far more profound than a missing piggy bank. The clause was discovered by a mathematician named Emmy Noether in 1918, and what she proved is one of the most beautiful results in all of science. She showed that conservation laws are not arbitrary rules handed down from on high. Each one comes from a symmetry, a way in which the universe stays the same when you change something about it. And the conservation of energy, she showed, comes from a very particular symmetry. It comes from the fact that the laws of physics do not change over time. If you do an experiment today, and you do the exact same experiment tomorrow, you get the same result, because the laws governing it are the same today as they were yesterday, and will be tomorrow. This sameness across time, this constancy of the rules, is what physicists call time translation symmetry. And Noether proved that wherever you have time translation symmetry, you get conservation of energy automatically as a mathematical consequence. The two are joined at the root. If the laws of physics are constant in time, energy is conserved. That is the real law. I find it helps to see this with an everyday picture before we turn it on the cosmos, because the idea that a symmetry produces a conservation law sounds abstract until you feel it. Imagine you are playing a game whose rules never change from one day to the next. Because the rules are fixed, you can plan. You can save up an advantage today and spend it tomorrow. You can count on a kind of fairness across time. That reliable fairness is what energy conservation is, in physics. It is the universe agreeing to play by the same rules at every moment, so that whatever you put in, you can get back out. Now imagine instead that the rules of the game quietly change between rounds, that the board itself grows larger while you play. Suddenly, there is no guarantee that the advantage you saved will still be worth the same tomorrow, because the very thing it was measured against has shifted. That is the situation of light in an expanding universe. The board is growing. The standard against which energy would be tallied is itself changing, and so the books are under no obligation to balance. You can even watch this play out in the numbers, in a way that makes the photons' plight especially stark. Ordinary matter, the atoms in galaxies, thins out as the universe extends, simply because the same amount of matter is spread through a larger and larger volume. That is a kind of dilution you might expect, and the total amount of matter is, in the simplest accounting, preserved even as it spreads. But light suffers a double loss that matter does not. Light thins out with the growing volume, exactly as matter does, because the photons are spread farther apart, and, on top of that, each individual photon is also redshifted, losing energy as its wavelength stretches. So the energy stored in light falls faster than the energy stored in matter, dropping away with an extra factor that matter never feels. In the universe's first epoch, when light dominated everything, this meant the radiant energy of the cosmos was draining away at a tremendous rate even as the universe was at its most brilliant. The light was already losing, already fading, already handing its energy back to a universe that kept none of it, long before there was a single atom or star to witness the loss. Now watch what happens when we point this at the universe as a whole. The conservation of energy depends on the laws of physics being unchanged over time, on the universe looking the same from one moment to the next. But the universe does not look the same from one moment to the next. The universe is expanding. It is larger today than it was yesterday, and it will be larger tomorrow than it is today. The stage itself is changing, growing, evolving in a way that has a definite direction in time. And when the thing you are studying is changing over time in this fundamental way, when the universe itself does not have time translation symmetry, the condition that guarantees energy conservation is simply not met. The link that Noether discovered is broken, and so, on the scale of the entire expanding universe, there is no law that requires the total energy to stay the same. I want to let that sit, because it runs against an instinct so strong that even physicists found it hard to accept. There is no piggy bank. There is no hidden account where the light's lost energy is stored. The energy of our redshifting photon is not transferred to space. It is not converted into the expansion. It is not handed to dark energy or to gravity or to anything else. It is simply not conserved. The universe took it, in the sense that the stretching of space drained it away. But the universe did not put it anywhere, because on this scale, the universe is under no obligation to keep the books balanced. The light gave up its energy to nothing at all. If you find this difficult, you are in excellent company, and you are reacting exactly as you should. The conservation of energy is one of the most successful ideas in the history of thought. It has never failed in any laboratory, in any engine, in any chemical reaction, in any collision of particles, and it has not failed in those places now. This is the subtle, important part. Energy is still perfectly conserved locally, in any small patch of the universe, in any experiment you could actually perform, in any region small enough that the expansion does not matter. Your coffee still cools the way it always has. The sun still shines by the rules. No engine will ever run on this loophole. What fails is only the attempt to add up all the energy across the entire expanding universe and demand that the grand total never change. That global total is not protected by any law, because the universe as a whole lacks the symmetry that would protect it. We have circled this strange fact before, from the other side. There is a companion question to tonight's, one that asks not where the light's energy goes when the universe drains it, but where the universe finds the energy to keep expanding in the first place, especially the energy that seems to fill empty space and drive the expansion faster and faster. And the answer there is the mirror image of the answer here. In both cases, the resolution is the same. The universe does not have a fixed energy budget that must be balanced. Energy can drain away with the stretching of light, and energy can appear with the stretching of space. And neither one breaks a law, because the law that would forbid it was never universal to begin with. It only ever applied where the rules of physics hold still, and the universe, taken as a whole, does not hold still. So we have our first real answer to a piece of tonight's question, and it is stranger than the question deserved. The oldest light has lost all of its energy, and that energy did not go anywhere. It was not destroyed in any violent sense, and it was not stored anywhere we can point to. It simply faded out of the ledger, the way a sustained note fades out of a song, not by going somewhere else, but by gently ceasing to be as loud as it was. The light has been quietly handing its energy back to a universe that does not keep it, does not store it, does not give it back, and is not even keeping count. But notice what this does and does not tell us. It tells us that the energy is gone, truly gone, and that this does not break any law. It does not tell us that the light is gone. Those are two different things. And the difference between them is the thing that saves our photon from death. Because here is the question that the energy story leaves dangling, and it is the most important question of the night. If the light has lost almost all of its energy, is the light still there at all? Has the photon, drained to 1,000th of its birth energy, finally winked out of existence? Or is it still travelling, still real, still a photon, just a colder and fainter one than it used to be? The answer is going to be the turning point of the whole story, and it is going to tell us, at last, whether light can die. Part 6. It did not die, it faded. Here is the turning point. The light is still here. After almost 14 billion years of stretching, after losing more than 99.9% of the energy it was born with, after fading from a warm glow into a cold microwave hum, our photon is still a photon. It still exists. It is still travelling at the speed of light. It still carries a wave, still has a wavelength, still does everything a photon does. It did not wink out. It did not reach zero and vanish. It was drained almost to nothing, and yet it remains, because losing energy is not the same as ceasing to exist. A photon with very little energy is still a photon, and so the oldest light in the universe, against every expectation that the word draining might raise in your mind, is not dead. It is everywhere. It is all around you. There are, as I told you at the start, about 411 of these surviving relic photons in every cubic centimetre of space, and that number is not a count of how many used to be there. It is how many are there right now, today, this instant, still going. Try to hold the totals in your mind for a moment, because they are part of what makes this light so easy to overlook and so impossible to escape. 411 photons in a volume the size of a sugar cube does not sound like much, but widen your view to the room, and you are surrounded by trillions upon trillions of them at every instant. Widen it to the sky, to the observable universe, and the count of relic photons climbs past anything the human mind can picture, a number with more zeros than there are grains of sand on every beach on Earth by an enormous margin. And here is the part that resets your sense of what the universe is made of. All the light from all the stars in all the galaxies that have ever shone, gathered together across all of cosmic history, is a faint sprinkle against this background. By sheer count, the universe is not a place of starlight with some leftover glow in the gaps. It is a place of ancient relic glow, with a thin scattering of stars lit here and there on top of it. The oldest light is not a faded remnant clinging on at the edges. It is the main event and always has been. And as I said at the very start, you may have already met it without knowing. On an old television tuned to a channel with no broadcast, that storm of static snow on the screen was fed by many sources, but a small and genuine fraction of it, roughly 1 part in 100, was the cosmic microwave background itself, relic photons from the clearing of the fog, ending their journey of almost 14 billion years by jostling the electronics of a television set. People all over the world sat in front of that snow and saw nothing but a broken signal, and reached over to change the channel, never knowing that a sliver of the noise was the oldest light in existence, arriving from the birth of everything to flicker for an instant on a screen in their living room before they tuned it away. I want to give you the truest single sentence I can about what happened to the oldest light, the sentence I would want you to remember if you remember nothing else from tonight. The light did not die, it faded. Those 2 words point at very different things, and the universe chose the gentler one. To die would be to stop existing, to wink out, to be gone. To fade is to grow dimmer and cooler and quieter while remaining, fundamentally, present. Our light faded. It is still the original light, the same photon set free at the surface of last scattering, but cooled now from the warmth of an ember to a temperature of 2.7 Kelvin, less than 3 degrees above the coldest temperature that can exist. The fire went out in the sense that the warmth is gone, but the glow, somehow, is still here, and there is something almost miraculous about the way it faded, a detail that turns out to be one of the most important clues in all of cosmology. So let me draw it out slowly. When a hot object glows, it does not glow at a single pure wavelength. It glows across a whole spread of wavelengths, a specific and predictable spread that depends only on its temperature. Physicists call this a blackbody spectrum, and it has a precise mathematical shape. A hotter object's spectrum peaks at shorter, bluer wavelengths. A cooler object's spectrum peaks at longer, redder wavelengths, but the overall shape, the characteristic curve, is always the same family of curve, just shifted by temperature. The early universe, glowing at 3000 degrees, had a perfect blackbody spectrum, the natural glow of hot matter in balance with its own light. Now here is the remarkable thing. When you stretch a blackbody spectrum by expansion, when you redshift every wavelength in it by the same factor, you do not scramble it or distort it. You get another perfect blackbody spectrum, just at a lower temperature. The stretching preserves the shape exactly. So the relic light, which began as a perfect 3000-degree glow, should today be a perfect glow at a temperature about 1100 times lower, if cosmological redshift and nothing else is what happened to it. And when we measure the cosmic microwave background, when we actually look at the spread of wavelengths in the oldest light, that is precisely, exquisitely, what we find. The cosmic microwave background is the most perfect blackbody spectrum ever measured anywhere, by anyone, in any context. It matches the ideal curve to better than 1 part in 10,000 across its entire range. It is more perfect than any glow we can produce in a laboratory. Think about what that perfection is telling us. The light travelled for almost 14 billion years across the entire history of the universe, through the forming of galaxies and the weaving of the cosmic web, and it arrived with its black body, shape flawlessly intact, simply cooled. Nothing scrambled it, nothing scattered it into a mess, nothing distorted the curve. Whatever drained its energy did so with perfect, uniform gentleness, taking exactly the same proportion from every photon, exactly as the stretching of space, and nothing else would do. The fading was clean. The light cooled the way an entire universe cools when it expands, evenly, smoothly, without violence, preserving its essential nature even as it gave away almost all of its warmth. This is the place in the story where I want to stop and let the weight of it land, because it is easy to hear all of this as abstract physics and miss what it actually means for you, sitting where you are. The light that has been falling on you your entire life is older than the sun. It is older than the earth. It is older than every atom of carbon and oxygen and iron in your body, all of which were forged inside stars that did not exist when this light was born. This light is the afterglow of the birth of the universe itself, the literal leftover radiance of the moment the cosmos became clear, and it is not a fossil sealed away in distant space where no one can reach it. It is here. It is in the room. 411 of these ancient photons sit in every sugar cube of space around you, and a faint, ceaseless patter of them is ending its journey of almost 14 billion years against your skin and your eyes and the walls of the room, right now, and again now, and again. You have been bathed in the cooling glow of creation every second of your life, awake and asleep, and you have never felt a thing. That is the strangeness I want you to carry forward into the rest of the night. Not that the light is old, although it is almost unimaginably old. The strangeness is that it is old and still arriving. It is ancient and still here. It faded almost to nothing, and yet it never stopped, and it is touching you now. The oldest thing in the universe is also one of the most present things in your life, and the two facts sit together in a way that should make the back of your neck prickle. But I have been telling you all of this as though we simply know it, as though the temperature and the perfection of the spectrum and the count of photons per cubic centimeter were facts we could read off the universe like a label. We can now. But for most of human history, we had no idea this light was here at all, and the way we became sure of it, the way we proved that the oldest light loses its energy to the expanding universe rather than to some other cause, is a story worth telling carefully, because it is also the story of how we ruled out the most tempting wrong answer. Before we can fully trust that the light faded the way I have described, we have to deal with the possibility that something else entirely is going on. Part 7. The Proof Written Across the Sky. I have been telling you that the oldest light lost its energy to the expansion of space, but I want to be honest with you about something, because intellectual honesty is the whole point of looking at the universe carefully, rather than just telling ourselves pretty stories. There has always been another explanation on the table, a simpler sounding one, and for a long time a reasonable person could have preferred it. If you do not like the idea that space itself is expanding and stretching light, there is an alternative that lets you keep a calm, static universe. It is worth understanding, both because it is tempting and because the way we ruled it out is one of the most satisfying detective stories in science. The alternative is called tired light. The idea was first floated in 1929, around the time we were just discovering that distant galaxies are redshifted, that their light is stretched toward the red. The mainstream explanation, then and now, is that the galaxies are receding because space between us and them is expanding, stretching the light on its way. But tired light offers a different story. What if space is not expanding at all? What if the universe is static, fixed, unchanging, and the redshift of distant light has nothing to do with stretching space? What if, instead, light simply gets tired as it travels? What if a photon, crossing the immense distances between galaxies, gradually loses a little energy along the way, bumping into something, leaking energy to the medium it passes through, so that the farther it travels, the more energy it loses, and the more redshifted it appears? You can see the appeal. Tired light keeps the universe simple and intuitive. Nothing has to expand. Space stays the comfortable, fixed stage we naturally imagine. The redshift becomes just a gradual tiredness, an aging of the light as it crosses great distances, with no need for the strange idea that the arena itself is growing. If tired light were correct, then the energy lost by our oldest photon would have a perfectly ordinary destination. It would have leaked into whatever the light was bumping against, and the conservation of energy would be safe, and the unsettling business of the broken ledger from the last part would simply evaporate. For a static universe with tired light, energy is conserved in the comfortable old way, so why do we not believe it? Why are physicists so confident that the universe really is expanding, and that tired light is wrong? The answer is that tired light makes predictions, and those predictions fail in 3 separate and independent ways, and the oldest light itself delivers 2 of the 3 verdicts. This is where the cosmic microwave background stops being just a beautiful relic and becomes a courtroom witness. Consider the first test. Any mechanism that makes light lose energy by bumping into things along the way, any real physical interaction that drains a photon, would also tend to knock the photon slightly off course. A little energy lost usually means a little change in direction, and if photons coming from a distant galaxy were each nudged off course by a tiny random amount on their long journey, the image of that galaxy would be blurred, smeared out, fuzzy. The farther away the galaxy, the more tiredness, and so the more blur. But that is not what we see. We see distant galaxies sharp and clear, their fine structure intact across billions of light years. The light arrives focused, not smeared. Tired light predicts a blurry universe, and the universe is not blurry. That is the first failure. Consider the second test, and this one is delivered by our oldest light directly. We just spent the last part marveling at the fact that the cosmic microwave background is a perfect blackbody spectrum, the most perfect ever measured. Now ask what tired light would do to that spectrum. If photons were losing energy by bumping into matter scattered through space, that scattering would not affect every photon by exactly the same proportion. It would distort the spectrum, dragging some parts of the curve more than others, smearing the clean blackbody shape into something lumpy and irregular. But the cosmic microwave background is not lumpy or irregular. It is flawless, clean to better than 1 part in 10,000. The only thing that preserves a blackbody spectrum perfectly while cooling it is the uniform stretching of space, taking exactly the same proportion from every photon. The perfection of the oldest light is, all by itself, a refutation of tired light. The light's own clean fade is the fingerprint of expansion. It is worth knowing just how hard we have looked at this spectrum, because the perfection is not a casual impression, but one of the most precise measurements ever made of anything. The trouble is that our own atmosphere glows and absorbs in the microwave band, so to see the oldest light cleanly you have to get above the air. In the early 1990s, a satellite carried an instrument above the atmosphere specifically to measure the spread of wavelengths in the cosmic microwave background, and it compared that spread, point by point, against the ideal mathematical curve that a perfect glowing body should produce. The measured points fell onto the ideal curve, so exactly that, when the results were first shown to a room of scientists, the error bars, the little marks showing the uncertainties listed in each measurement, were smaller than the thickness of the line drawn for the theoretical prediction. The audience applauded. They were looking at the most perfect natural glow ever recorded, and it matched the prediction for cooled, expanded relic light to a precision that no tired light scrambling could ever survive. The people who made that measurement were later given the Nobel Prize, and rightly so, because they had turned the oldest light from a faint curiosity into a courtroom exhibit of extraordinary power. There is a fourth quiet test as well, one that has been used on distant galaxies, and that tired light fails just as badly. In a genuinely expanding universe, the apparent surface brightness of a distant object, the amount of light coming from each patch of its image, should dim with distance in a very specific and rather dramatic way, far more steeply than in a static universe. Astronomers can measure this, comparing how the brightness of galaxies' surfaces falls off with redshift, and the measurements match the steep dimming that expansion predicts, not the gentler fall-off a static tired light universe would show. Test after test, on the oldest light, and on distant galaxies, and on exploding stars, the verdict is the same. The universe expands, the light fades by stretching. There is no quiet leak, no comfortable account where the lost energy waits. The strange answer holds. And consider the third test, the one I find the most beautiful, because it turns distant exploding stars into cosmic stopwatches. When a certain kind of star explodes as a supernova, it brightens and fades over a span of days to weeks, in a pattern we understand very well. Now, if the universe is expanding, then time itself appears stretched for distant events, just as the light is stretched. A supernova far away, at high redshift, should appear to play out in slow motion, taking longer to brighten and fade than a nearby one, by exactly the factor its light is redshifted, and that is precisely what we observe. A supernova whose light is doubled in wavelength takes twice as long to rise and fall as a nearby one. The distant universe is running in slow motion, exactly as expansion predicts, and tired light does not. Tired light has no reason at all to stretch the duration of an explosion. Only a genuinely expanding universe, stretching time along with space, can do that, so tired light fails 3 times over. The universe is sharp, not blurry. The oldest light is a perfect black body, not a distorted one. And distant explosions run in slow motion. All 3 point the same way. The universe really is expanding, and our photon really did lose its energy to the stretching of space and to nothing else, and the unsettling answer from before stands. The energy is gone, paid into no account, and the only thing that drained it was the growth of the cosmos itself. This is what I love about the oldest light. It is not just a relic to admire. It is the central piece of evidence, the cleanest fingerprint, the proof written across the entire sky that the universe expands and that light fades by stretching rather than by tiring. The cosmic microwave background is both the patient and the diagnosis. It is the oldest light, and it is the reason we understand what happened to it. But now I want to return to our photon and ask a question that has been waiting quietly in the background since the beginning. A question that has nothing to do with energy or expansion and everything to do with time. We have been saying our photon is almost 14 billion years old. We have been following it across the entire history of the universe, as though it has lived through all of that history, enduring the long dark, waiting out the eons. But there is a sense, a real and rigorous physical sense, in which our photon has not experienced any of it. There is a sense in which the oldest light in the universe is, to itself, no time old at all. And that is one of the strangest truths in all of physics. Part 8. The Clock That Never Started. I have to introduce one of the strangest results in all of physics now, and I want to lead you to it gently, because it overturns something so basic that we never even think to question it. We assume that time passes at the same rate for everything. We assume that if our photon has been travelling for almost 14 billion years by our reckoning, then it has experienced almost 14 billion years, the way we would experience a long journey. But that assumption is wrong, and the way it is wrong is bound up with the very thing our photon is, a particle of light moving at the speed of light. One of the foundations of modern physics is that time does not pass at the same rate for everyone and everything. Time is not a universal clock ticking the same everywhere. The rate at which time passes for something depends on how it is moving. The faster something travels through space, the slower its own clock ticks, as measured by someone watching from outside. This is not a trick of perception or a flaw in our instruments. It is how the universe is built. A clock moving very fast really does tick slowly compared to one sitting still. We have measured this directly with precise clocks flown on aircraft and carried up tall buildings and accelerated in laboratories, and it is true every time. Motion slows time. Now push that idea to its limit. As something moves faster and faster, approaching the speed of light, its own clock ticks slower and slower compared to the outside world, and at the speed of light itself, the limit, the clock does not tick at all. Time, for something moving at the speed of light, does not pass. This is why nothing with mass can ever quite reach the speed of light, but light itself always travels at exactly that speed, and so light lives at the limit where time stands still. For a photon, there is no passage of time. There is no ticking clock. From the photon's own point of view, if we can even speak of such a thing, no time elapses between the moment it is created and the moment it is absorbed, no matter how far it travels or how long that journey takes by our clocks. Let that turn over in your mind, because it applies directly to our oldest light. From our point of view, sitting here in our galaxy almost 14 billion years after the surface of last scattering, our photon is the oldest thing we will ever encounter. It has crossed almost the entire history of the universe. But from the photon's own point of view, the journey took no time at all. The moment the fog cleared and it was set free, and the moment, billions of years later, when it finally strikes a detector or a human eye, are not separated by any experienced duration. They are, for the photon, the same moment with nothing in between. The long stretch we described, the slow reddening across the eons, the waiting out of the dark ages, and the forming of galaxies, all of that happened in our time, in the time of the world the photon travels through. In the photon's own time, it did not happen at all, because there is no photon's own time. There is no clock. There never was. I want to sit with this, because it is the place tonight where the universe is at its most quietly astonishing. You are the photon, one final time. From the outside, you are almost 14 billion years old, the most ancient traveller in existence, carrying the universe's oldest memory across the gulf of cosmic time. But from the inside, there is no inside. There is no clock running. There is no long wait, no enduring of the dark, no counting of the years. The instant you were set free from the fog, and the instant you finally end your journey against some surface are, to you, a single instant, pressed together with nothing between them. You did not travel for billions of years. You did not travel for any time at all. The longest journey in the universe took, from your own point of view, no time whatsoever. You are ancient and you are ageless. And these are not two facts in tension. They are the same fact, seen from two sides. This is the second great strangeness of the oldest light, sitting right alongside Zayn the First. We said before that the light is old and still arriving, present and ancient at once. Now we can add that the light is ancient and unaged at once. The oldest object you will ever encounter has not, by its own reckoning, aged a single second since the universe was an opaque fog. It carries the imprint of the newborn cosmos, not because it has preserved it carefully across the eons, but because for the light, almost no eons have passed. The surface of last scattering is, in the photon's own frame, almost no time ago. The birth of the universe is, for the light, almost now. So what does it even mean to ask whether such a thing can die? A photon does not age. It does not wear out. It does not decay from the inside, growing old and brittle the way living things do, because it does not experience the passage of time that aging requires. Left entirely alone, undisturbed, a photon would travel forever, unchanged in its own frame, as young at the end of time as it was at the beginning. The only things that can happen to a photon are things done to it from the outside. It can be absorbed, handing its energy to matter and ceasing to be light. It can be stretched by the expansion of space, fading in energy while remaining itself. But it cannot simply grow old and die. There is no internal clock to run down. In this sense, light is closer to immortal than anything else in the universe. You might wonder whether a photon could decay anyway, the way an unstable particle does, splitting after some span of time into something lighter. Many particles do exactly that. A free neutron, left alone, falls apart in about 15 minutes. Heavier particles can vanish in tiny fractions of a second. So could a photon, given long enough, simply come apart? The answer, as far as we can tell, is no, and the reason is elegant. For a particle to decay, there has to be something lighter for it to decay into. A neutron can fall apart because there are lighter particles waiting to carry away the pieces. But the photon is, as far as we know, perfectly massless, which means there is nothing lighter than it anywhere in nature. There is no rung below it on the ladder. With nothing to decay into, the photon has no way to fall apart, and so it endures. Physicists, being careful people, have tried to test even this, because a perfect zero is hard to prove, and you can only ever set a limit. They have asked what would happen if the photon had not exactly zero mass, but some unimaginably tiny one, just enough to allow a slow decay, and they have turned the unchanging spectrum of the oldest light into an answer. If the photon could decay at all, the analysis shows a particle of visible light would need to survive in its own frame for something like 1 billion years before falling apart, a span so far beyond the present age of the universe that it makes the word lifetime almost meaningless. And, because of the time-freezing effect we just discussed, photons crossing the cosmos to reach us are even more protected than that figure suggests, since in their own frame almost no time passes at all. So from every direction we look, the verdict is the same. The photon does not decay. It does not age. It does not come apart. Whatever is going to happen to the oldest light, it will not be a death from within. The only thing that can take a photon is the universe acting on it from the outside, and the gentlest of those actions, the stretching of space, does not kill it either. It only fades it, and yet we have spent the whole night watching the oldest light fade, watching it lose almost all of its energy, watching it cool toward the cold. So we have arrived at the central paradox of tonight, stated as sharply as I can state it. Light is, in its own frame, ageless and very nearly immortal, and at the same time the oldest light has faded almost to nothing. How can both be true? How can something be immortal and fading at once? Holding those two truths together is the key to the whole question of whether light dies, and we are nearly ready to put them together. But first we have to confront a limit, a wall, that the oldest light marks for us, a wall that tells us this light is not just old but is, in a precise sense, as far back as light can ever take us. Part 9. The wall at the edge of sight. There is a hard limit built into everything we have been discussing, and it is time to face it directly, because it explains why the oldest light is the oldest light, why there is nothing older for us to ever see. The cosmic microwave background comes from the surface of last scattering, from the moment the fog cleared at 380,000 years. And that moment is not just the birth of our photon. It is a wall. It is the earliest thing that light can ever show us, the deepest into the past that any telescope, no matter how powerful, will ever be able to look. To understand why, we only have to remember what the early universe was like before the fog cleared. Before recombination, the universe was opaque. It was that glowing plasma, that fog of free electrons, in which light could not travel in a straight line. So if you point the most powerful instrument ever built at the sky and try to look back in time, back toward the beginning, you can see clearly all the way back to the moment the fog cleared, and then you hit the fog, and you can see no further. The cosmic microwave background is the light from the surface of that fog, the last clear thing before the opaque wall. Trying to see past it with light is like trying to look into the center of a thick cloud or into the glowing body of a star. The light from farther inside cannot reach you because it scattered away before it could escape. The surface of last scattering is, quite literally, the edge of the visible universe in time. It is the wall at the edge of sight. This is a profound limitation, and it is worth feeling the full force of it. Everything we can ever see with light, every galaxy, every star, every relic photon, comes from after the fog cleared. The first 380,000 years of the universe, the era when the most violent and formative events of all took place, the era closest to the Big Bang itself, is hidden behind a curtain of light that scattered before it could carry its story out to us. We cannot see the beginning. We can only see the moment the universe first became clear and infer the rest. The oldest light is the oldest precisely because it comes from this wall, and there is no light from before it, anywhere, that we will ever catch. But I do not want to leave you thinking the wall is the absolute end of what can be known, because it is not, and the way around it is one of the most exciting frontiers in all of science. Light is not the only messenger the universe sends. It is only the most familiar one, and there are other messengers that were able to escape the early universe long before light could, messengers that passed through the fog, as though it were not there, carrying news from epochs that light can never reach. Consider the first of these other messengers, the ghostly particles called neutrinos. Neutrinos barely interact with anything. They pass through ordinary matter as though it were empty space, trillions of them streaming through your body every second without touching a single atom. In the early universe, this aloofness meant that neutrinos stopped scattering, stopped being trapped, and began travelling freely, not at 380,000 years, like light, but at about 1 second after the Big Bang. There should be, filling the universe right now, a cosmic neutrino background, a sea of relic neutrinos set free when the universe was 1 second old, carrying an image of an era light can never show us. Detecting it directly is one of the great unsolved challenges of physics, because the same aloofness that let the neutrinos escape so early makes them maddeningly hard to catch. But they are there, almost certainly, an even older relic than the oldest light, an earlier layer of the past waiting just beyond the wall. We can even estimate their temperature today, cooled by the same expansion that cooled the light, and it comes out a little colder than the cosmic microwave background, somewhat under 2 degrees above absolute zero, with a few hundred of these relic neutrinos packed into every cubic centimetre of space alongside the relic photons. 2 oceans, then, fill the universe at once. One of light, which we can see, and one of neutrinos, older and even fainter, which we cannot yet catch, but which is streaming through you at this moment, just the same. The difficulty of detecting that neutrino C is worth dwelling on, because it shows how the same property can be both a gift and a curse. The very aloofness that let the neutrinos escape the early universe so soon, passing through the fog as though it were not there, is exactly what makes them so nearly impossible to stop now. A relic neutrino from 1 second after the beginning carries so little energy, after all the cooling, that getting it to leave a mark in any instrument is one of the hardest challenges anyone in physics has ever set themselves. Schemes to do it exist on paper, clever and demanding, and one day one of them may succeed. If it does, we will hold in our hands a signal from the universe at 1 second old, a message from an epoch the oldest light can never reach, and the wall at the edge of sight will have been quietly stepped around. Until then, the neutrino sea remains a near certainty we cannot yet touch, a presence inferred from everything we understand about the early universe, but never directly heard. And consider the other messenger, perhaps the most tantalizing of all, gravitational waves. These are ripples in the fabric of space itself, and they too pass through matter almost untouched. Ripples in space from the very first fraction of a second after the Big Bang, from the violent era when the universe may have undergone a burst of explosive expansion, should still be propagating through the cosmos today as a primordial gravitational wave background. These ripples would carry information from a time unimaginably closer to the beginning than even the neutrinos, from the first tiny sliver of a second of existence. We have only recently learned to detect gravitational waves at all, from colliding black holes and neutron stars, and detecting the faint primordial background from the birth of the universe is a goal that may take generations. But if we ever do, we will have seen past the wall that light can never cross. So the oldest light defines a boundary, and standing at that boundary changes how you think about it. The cosmic microwave background is not just an old relic. It is the edge of one kind of sight, the farthest back that light itself can carry us, the last clear image before the universe closes into fog. It is the oldest light precisely because it sits at that wall. And knowing that there are older messengers beyond it, neutrinos and gravitational waves, whispering from epochs light can never reach, only deepens the strangeness of the light we can see. The oldest light is old and ageless, and still arriving, and now we can add that it is the farthest thing back that light will ever show us, a glow from the surface of the wall at the edge of time. We have been talking about all of this as though we have always known the oldest light was there, but we have not. For almost all of human history, no one had any idea that the afterglow of creation was raining down on them constantly. The story of how we finally found it is not a story of grand expeditions or careful searches. It is a story of two people trying to get rid of a noise they could not explain and stumbling, almost by accident, onto the oldest light in the universe. Part 10. The Hiss That Would Not Go Away. The discovery of the oldest light is one of my favourite stories in all of science, because it shows how the universe sometimes hands us its greatest secret when we are looking for something else entirely, and how easy it is to mistake the most important signal in existence for an annoyance. But before I tell you how it was found, I have to tell you that it was predicted, years earlier, by people who reasoned it out from pure thought, and then was almost completely forgotten. In 1948, a small group of physicists working through the consequences of a hot early universe realized something remarkable. If the universe began hot and dense and has been expanding and cooling ever since, then there should be a leftover glow, a relic radiation, still filling all of space, cooled by the expansion to just a few degrees above absolute zero. They even estimated the temperature, putting it at around 5 degrees above absolute zero, which is astonishingly close to the true value for a first guess made with almost nothing to go on. They had predicted the cosmic microwave background on paper, from reasoning alone, and then, for the most part, the prediction was set aside and forgotten. The tools to detect such a faint, cold glow did not obviously exist, and the idea drifted out of the conversation for nearly 2 decades. Now move forward to 1965, to a field in Holmdel, New Jersey, where 2 radio astronomers named Arno Penzias and Robert Wilson were working with a large, sensitive horn-shaped antenna, originally built for early satellite communication. They wanted to use it to make careful measurements of faint radio signals from the sky, and to do that, they needed to understand and eliminate every source of noise in their instrument. So they pointed the antenna at what should have been quiet, empty disks, and they listened. And they found a noise they could not get rid of. A faint, steady hiss of microwave static, coming in no matter where they pointed the antenna, present day and night, in every season, from every direction in the sky equally. It would not go away. I want you to picture their growing frustration, because it is one of the most human moments in the history of physics. It is 1965, and 2 careful, meticulous scientists are losing patience with a sound. The great horn antenna points at the empty sky, and through it comes a hiss, faint and steady and everywhere, refusing to be explained. They suspect their equipment first, as any good scientist would. They check the wiring, they check the electronics. They cool the components to reduce the noise from heat, and still the hiss remains. They wonder if it is the city of New York, glowing with radio noise on the horizon, so they point away from the city, and the hiss is unchanged. They discover that a pair of pigeons has been roosting inside the antenna, leaving behind what they politely call a white dielectric material, and they think, surely this is it, surely the birds and their mess are the source. So they evict the pigeons, they clean out the antenna, they scrub away the droppings, and they point the great horn back at the sky, and the hiss is exactly as it was before, faint and steady, and coming from everywhere, the same in every direction, unbothered by all their efforts. The noise will not go away because the noise is not noise. It is the oldest light in the universe, and it has been arriving the whole time. What Penzias and Wilson had found, without setting out to find it, was the cosmic microwave background. The afterglow of creation predicted 17 years earlier and nearly forgotten. The hiss they could not eliminate was the relic radiation of the early universe, cooled by billions of years of expansion to that faint microwave glow, arriving from every direction because it fills all of space. The reason it came in equally, no matter where they pointed the antenna, is that the oldest light is everywhere, surrounding us on all sides, the surface of last scattering wrapped around us like the inside of an enormous sphere. They had pointed their instrument at the birth of the universe by pointing it at nothing in particular, and the universe had answered with a whisper they spent the better part of a year trying to silence. When they finally connected with theorists who recognized what the signal was, the meaning became clear, and it changed cosmology forever. The faint hiss was the single strongest piece of evidence that the universe began in a hot, dense state and has been expanding and cooling ever since. It was the relic the 1948 prediction had described. Penzias and Wilson received the Nobel Prize for the discovery, an honor for a signal they had at first regarded as a problem to be solved. And in the decades since, we have studied the oldest light with extraordinary care. Satellites carried instruments above the atmosphere to measure it precisely, and it was those measurements that revealed the perfect black body spectrum we marveled at earlier, and the faint temperature ripples across the sky, variations of about 1 part in 100,000, that turn out to be the seeds from which every galaxy, including our own, would eventually grow. The oldest light is not only the afterglow of creation, it is also the blueprint of everything that came after, the faint pattern from which all structure in the universe was sown. Let me linger on those ripples, because they turn the oldest light from a relic into a kind of seed map, and they tie the whole story together. When we make a precise picture of the cosmic microwave background across the entire sky, it looks at first glance perfectly smooth, the same temperature in every direction to a remarkable degree. But when we sharpen the picture and look closely, we find that it is not perfectly smooth. There are faint patches that are very slightly warmer and faint patches that are very slightly cooler. Differences of only about 1 part in 100,000, a warmth or coolness so small you would never notice it without the most sensitive instruments. Those tiny patches are the most important imperfections in the universe. They are the imprint of the slight clumpiness of matter. At the moment the fog cleared, places where the early cosmos was a hair denser or a hair thinner than average, and gravity, given billions of years, took those faint clumps and pulled them together, the slightly denser regions drawing in more matter, growing into the first stars, the first galaxies, the great cosmic web of structure that fills the universe today. So when you look at a map of the oldest light, you are not only looking at the surface of last scattering, at the faded glow of the universe's first clear moment. You are looking at the seeds of everything, every galaxy that exists, including the one you live in, every star, every planet, every atom that ever gathered into a world grew from those faint ripples printed on the oldest light. The same glow that is fading is also the blueprint. The light that lost almost all its energy is the same light that carries the pattern from which all the structure you have ever known was sown. The afterglow of creation and the seed map of creation are one and the same thing, cooling quietly in every direction around you. There is something I find almost unbearably fitting about the way it was discovered. The most important light in the cosmos, the literal glow of the universe, did not arrive with trumpets. It arrived as static, as the snow on a television, as a hiss that 2 tired engineers wanted nothing more than to make stop. The afterglow of everything came disguised as noise, and once you know it is there, you can never quite hear silence the same way again, because there is no true silence. The faint hum of the beginning is always present, in every direction, in the empty channel and the quiet sky and the dark between the stars. So we have followed our photon from its birth in the fog to its discovery in a New Jersey field, and we have understood that it faded rather than died, that it lost its energy to a universe that does not keep the books, that it is ageless in its own frame and still arriving in ours. But there is one part of the story left, and it is the part that finally answers the question of whether light can truly die. Because so far, we have only followed the light up to the present day. We have not asked what happens to it in the future. We have not asked how this story is mismanned. And to do that, we have to leave the present behind and travel forward into the far future of the universe, to a time when the sky itself begins to empty. Part 11. The Sky That Empties. We have followed the oldest light from the beginning to now. To finish the story, we have to do something harder and stranger. We have to follow it into the future, far past our own time, into an era so distant that everything familiar about the night's sky will have changed. Because the question of whether light dies cannot be fully answered by looking at the past. It can only be answered by asking what happens to light at the end of time, and to do that, we need one more fact about our universe, a fact that changes the ending of the story. The expansion of the universe is not slowing down. You might have assumed that the expansion, like a ball thrown upward, would gradually lose pace, pulled back by the gravity of all the matter in the cosmos. For most of the 20th century, that is what many expected. But near the end of that century, careful measurements of distant exploding stars revealed something that stunned everyone who studied it. The expansion of the universe is not slowing down, it is speeding up. Some property of space itself, which we call dark energy for lack of a better name, is driving the galaxies apart faster and faster as time goes on. The universe is not coasting to a gentle stop, it is accelerating, and it appears that it will keep accelerating for as long as we can foresee. This changes everything about the fate of light, because acceleration means the stretching never stops, and in fact grows more aggressive with time. Think about what that does to our oldest light, the cosmic microwave background, going forward. We have watched it cool from 3,000 degrees to 2.7 degrees above absolute zero over almost 14 billion years. But the expansion is not finished with it. As the universe continues to grow, faster and faster, the relic light will keep stretching, keep redshifting, keep cooling. In a few tens of billions of years, it will drop below 1 degree above absolute zero, then below 1/10 of a degree, then below 1/100th. Its wavelength will grow longer and longer, its energy fainter and fainter, until, within something like 100 billion to 1 trillion years, the oldest light will be redshifted so far that no conceivable instrument could ever detect it. It will still be there, in the sense we have insisted on all night, still real, still arriving, still technically present. But it will be so cold, so faint, so stretched, that for any practical purpose it will have faded beyond reach. The afterglow of creation will have become undetectable, not by dying, but by fading past the threshold of anything that could ever notice it again. And the same fate, it turns out, awaits not just the oldest light, but all light. Here is where the acceleration does something truly haunting. The galaxies beyond our own low neighborhood are being carried away from us by the expansion, and because the expansion is accelerating, they are receding faster and faster. The light from those distant galaxies is being redshifted more and more severely as they recede, stretched toward longer and longer wavelengths, dimmer and dimmer, and eventually, for galaxies far enough away, the expansion carries them away so fast that their light can never reach us at all. One by one, over the coming tens and hundreds of billions of years, the distant galaxies will redshift toward invisibility, and then slip beyond the horizon of what we can ever see, their light stretched into oblivion before it can arrive. The sky will empty. A future astronomer, far enough ahead in time, would look out and see only the nearby stars of their own galaxy, and beyond that, nothing. No other galaxies, no cosmic microwave background, just darkness and the slow fading of their own local light. There is a boundary that makes this precise, and it is one of the strangest features of an accelerating universe. We are used to thinking that with a good enough telescope and enough patience, light from anywhere could eventually reach us. In a universe whose expansion is speeding up, that is no longer true. There forms a kind of edge, a distance beyond which the space is being carried away faster than light can cross it, so that anything past that edge can never send us a signal again, not in any amount of time, not ever. As the expansion accelerates, that edge draws inward, and more of the universe falls behind it, like a shoreline retreating as the tide carries the water out of reach. Galaxies we can see clearly will, over the coming tens of billions of years, drift past that boundary, their final light stretched toward infinite wavelength as they cross it, and then fall silent forever. They will not have gone anywhere violent. They will simply have been carried beyond the reach of light. The time scales here are almost numbing, and they are worth stating plainly so the slowness lands. Our own galaxy and its nearest large companion are bound tightly enough by gravity that the expansion will not tear them apart. Instead, they will drift together and merge into a single combined galaxy over the next several billion years, an island that holds against the spreading. But beyond that island, everything recedes. Star formation across the universe will sputter on for a long while, and then wind down as the raw gas is used up. And by something like 100 trillion years from now, the last new stars will have formed, and the era of starlight will be drawing to its close. The longest-lived of the small, cool stars will glow on faintly for trillions of years after that. The final fires in an emptying dark, until they too burn down to cinders. And through all of it, the oldest light, the cosmic microwave background, will go on, cooling and stretching in the background, fading past 1 degree, past a fraction of a degree, past any hope of detection, present to the end and unreachable long before it. I want to take you all the way to the end now, to the last light, because it is the moment that finally tells us what death means for a photon. Picture the universe 100 billion years from now, and then far beyond that. The other galaxies are gone from the sky, redshifted into silence, carried beyond the horizon. The stars are dying out, one by one, as the gas that makes them runs low, and the last of them burn down to embers. And somewhere at the very end of the age of starlight, a final star flickers and a final photon leaves its surface, setting out across a universe that is emptying and stretching faster with every passing moment. That photon travels, as photons always do, at the speed of light, never slowing, but the space it crosses is swelling beneath it, faster and faster, and its wave is stretching, lengthening, draining. Its wavelength grows past the microwave, past anything we have a name for, longer and longer, until a single ripple of it is stretched across a span greater than the distance light has travelled since it set out. It is not absorbed because there is nothing left to absorb it. It is not destroyed because nothing is there to destroy it. It simply travels, and stretches and fades, its energy creeping downward towards zero across an endless future, growing fainter forever, and never quite reaching nothing at all. That is the end of light, if it is an end, not a sudden death, not a winking out. An endless fading, an energy that approaches zero across infinite time but never actually arrives there. A glow stretched thinner and thinner forever in an expanding dark. The light does not die. It dims without limit and without end. Toward a nothing it never quite becomes. And so we have our answer, or as much of an answer as the universe is willing to give. But the answer is stranger and gentler than the question expected, and it deserves to be put together carefully, all the pieces at once, in the quiet at the end of the night. Part 12. The Universe's Longest Goodbye. So let us put it all together, slowly, the way you assemble the meaning of a long story, only once you have reached the end of it. We began with a simple question. Does light ever die? When the universe makes light, what becomes of it in the end? And we have followed a single photon, the oldest kind of light there is, from its birth in the clearing fog to its discovery as a hiss in a New Jersey field, and onward into the emptying sky of the far future. Now we can say what we have learned, and weigh whether the word death belongs to light at all. Here is the first truth. A photon does not die from within. It does not age, because it travels at the speed of light, and at the speed of light no time passes. It does not decay, because there is nothing for it to decay into, and no internal clock to run down. Left undisturbed, a photon would travel forever, as young at the end of time as it was at the beginning. In its own frame, light is ageless, and very nearly immortal. Nothing about light itself contains the seed of its own death. Here is the second truth, and yet light loses energy. As it travels across the expanding universe, the stretching of space drains its energy away, turn by turn, year by year, until the warm glow of the early universe has become a cold microwave whisper. That energy is not stored anywhere. It is not paid into any account. On the scale of the whole universe, energy is simply not conserved, because the universe, growing and changing in time, lacks the symmetry that would protect it. The light's energy fades the way a held note fades from a song, not by going somewhere else, but by gently ceasing to be as loud as it was. And here is the third truth, the one that resolves the paradox of the first two. Losing energy is not the same as dying. The photon, drained to 1,000th of its birth energy, is still a photon, still real, still travelling, still here. The oldest light is not a memory or a fossil. It is the original light itself. 411 photons in every sugar cube of space around you, still arriving, still cooling, having faded almost to nothing, and yet never having stopped. So the most honest answer to whether light dies is the one I gave you in the middle of the night and can now give you with all its weight. The light does not die, it fades. Hold those two words apart one last time, because the whole story lives in the difference between them. To die is to stop, to end, to be gone. To fade is to grow dimmer and cooler and quieter while remaining, fundamentally, present. The universe, given the choice between those two fates for its light, chose the gentler one and made it endless. The oldest light fades, the last light will fade. And the fading is not a single event, but a process without end. An energy approaching zero across infinite time and never arriving, a glow stretched thinner and thinner forever in an expanding dark. Light does not die. It gives its energy away to a universe that does not give it back, fading without limit and without ending, present to the last. I told you, at the very beginning, that this light is the universe's longest goodbye, and now you know why. A goodbye is not a death. It is a long, slow leaving, a fading of presence that can stretch out far longer than the thing it is ending, and this goodbye is the longest there is. It began before there were any eyes to see it, in the clearing of a fog almost 14 billion years ago. It is still going on now, in the faint patter of relic photons against your skin as you listen, and it will go on long after the last star has burned out, long after the sky is emptied, long after there is anyone left to say goodbye to, the last photons stretching outward forever in the dark, fading toward a silence they never quite reach. The oldest light will outlast the stars. The last light will outlast everything, and neither one will ever truly be gone. I find something steadying in that, something I want to leave you with as the night winds down. We tend to think the universe is a place that destroys, that everything ends, that all things pass into nothing. And it is true that the universe keeps nothing forever, that even the brightest glow is drained away in the end. But it is also true that the universe destroys nothing completely. The light that was set free at the beginning is still here. It faded almost to nothing, and it is still here. The energy left the ledger, and the light remained. The universe keeps nothing and loses nothing all at once, and the proof of it is the gentlest thing imaginable. A glow just under 3 degrees above the coldest cold there is, filling all of space, arriving from every direction, still saying, after almost 14 billion years, a goodbye that is in no hurry to be finished. There is a kind of comfort in this that I did not expect when I first sat with it, and I want to offer it to you plainly. We are surrounded, always, by endings. Things wear out, people leave, the warmth goes out of what once felt permanent, and it is easy to carry the quiet belief that the universe is in the business of erasing, that everything is finally headed for nothing. The oldest light gently disagrees. It shows us a universe that does let go of things, that drains away even the brightest glow until almost nothing of its energy is left, and yet does not erase. The letting go and the keeping happen together. The light is nearly emptied of energy and still entirely here. The goodbye is real, and it is also unfinished, and it will stay unfinished longer than the stars themselves last. If the universe can hold on to its very first light this gently, fading it for 14 billion years, and counting without ever quite letting it go, then perhaps endings in this universe are softer and slower and less complete than they appear from the inside of a single short life. And there is one more thing the oldest light has been doing this whole time, quietly, while we talked. It has been arriving, not as a finished event in the past, but as a present tense fact, continuous and ongoing. Every second you have been listening tonight, relic photons from the clearing of the fog have been ending their journeys against you, against the walls, against the sky, by the countless trillion, the way they did a second ago, and the way they will a second from now. The oldest light is not a thing that happened. It is a thing that is happening to you right now, and it will go on happening, growing fainter by an immeasurable amount with each passing age, for a span of time that makes the entire history up to this moment look like the first breath of a very long life. So the next time you find yourself somewhere quiet, in a dark room, under a clear sky, in the static of an empty channel, remember that you are not alone in the silence. The oldest light in the universe is there with you, as it has been your whole life, raining down softly from every direction the cooled and faded radiance of the moment everything became clear. It did not die, it faded, and it is still arriving. It will be arriving for a long, long time. And that, in the end, is what happened to the oldest photons in the universe. They are not gone. They are simply, endlessly, on their way out, taking the longest goodbye there has ever been or ever will be.